Hi everyone. So today we're going to work on identifying some of the properties of rational functions. Now keep in mind rational functions, and sometimes you'll hear me say reciprocal functions, basically mean that the variable is in the bottom of the fraction, like 1 over x. And these are just variations of that. So let's define what a rational function is. It's a function that can be written in the form f of x of p of x over q of x, or p and x and q and x are polynomials. Now, the big concern is the denominator. Remember, we cannot have 0 in the bottom of a fraction because we cannot divide by 0. We don't know what that is. It's undefined. So the domain of our function is all the real numbers except where q of x cannot be equal to 0. Okay, so some examples of rational functions would be, and we can use y and not f of x. That's perfectly fine. Would be x squared plus 1. Or y equals, let's do x plus 3 times x plus 2 all over x plus 2. And let's do one more. Let's do y equals, let's go x plus 4 over x minus 2. Okay? So these are all rational functions. They all are fractions. Each to top is a polynomial, the bottom is a polynomial. And we just have to be concerned about where is that polynomial equal to 0 for the domain. Okay? All right. So we have some terms that we need to talk about, and whether or not the graph is continuous, discontinuous. If it's discontinuous, it has points of discontinuity. Is it removable discontinuity? Or non-removable discontinuity. So we need to define what does it mean to be continuous and discontinuous. All right, so I have my calculator here, and I apologize, I have to leave it up, otherwise the app shuts down. So we're just going to be living with the calculator today. All right, so I'm going to graph the first one. So I already have it in here. Notice that there's parentheses around the denominator. You have to use those parentheses if you're going to use your calculator to graph to help you, because otherwise it's not going to do it correctly. It will divide the x squareds first, then add the 1, so you're just going to get a horizontal line at 1. That's all it would be because the x squareds would cancel out. So I have that in there, and if I press graph, we get this really funky looking graph where it looks like a really weird quadratic. And if you look, it looks like the y equals 1 almost looks like a horizontal axis because it doesn't look like the graph hits that. All right, in the second one, let's go back and we put that one in and see what that looks like. I'm going to put a bunch of parentheses in here. And then tell the top divided by the bottom. Okay, and believe in the parentheses because it tells you the grouping. So we're going to graph that. And how did that become a straight line? Oh, well, that's certainly weird. Looks like its y-intercept is 3. And let's use a different color here. And it looks like it somewhere intersects the x-axis, I think. I'm not sure. Where do I have it? Oh, somewhere around 3, I think. Okay, so there's the x and y-intercept. Negative 3 here. Well, that's weird. We'll have to look at that some more. And then our last graph would be y plus x plus 4 divided by x minus 2. Oh, look at that. It looks like we have some asymptotes here. Remember we talked about asymptotes the other day. It definitely looks like we have a vertical asymptote, and I do believe that's going to happen at 2. And it does look like we have a horizontal asymptote at 1. Let's see. Yeah, it looks like 1. And let's see it. I'm not very good at these graphing wise. There we go. Looks with our two branches. All right, so which one of those three graphs did I graph without jumping? Okay, because they don't have any holes or breaks. And that's definitely the first one. So this first graph would be continuous. Okay, now the reason why that's continuous, right, that was not good of me to just draw it right over top of that. Okay, let's do that again. All right. There. Okay, so that's definitely a continuous graph because I didn't pick up my pencil when I drew it. Now the second one definitely looks like okay, the second one, okay, the x plus 3, x plus 2, definitely looks like it would be continuous, but we have a problem. Let's look at the table. If I'm looking at the table, right here at -2, it says NaN. And that's a problem because at -2, if I put -2 into the problem, I'm going to get undefined. Okay, even though this graph looks like it's continuous, it actually is discontinuous because it has what is called a hole. This has a hole. Okay, so we're going to talk about where that comes from. All right, but basically, if you can take a look, you see how these two can cancel each other out? Yeah, -2 is part of the original function, but it's not part of the reduced function, but we'd have to indicate that by doing a hole, and we'll talk about that. But that is actually removable discontinuity, where we can reduce the function and it creates a hole in the line. Okay? And then the last graph would definitely be discontinuous. Because I do have the vertical and horizontal asymptotes. And it's not removable because I can't reduce the function. Okay? So the first one is continuous. Then the second two are both discontinuous. The first one has a hole, which is removable discontinuity. The second one is just non-removable discontinuity because I can't reduce it. The second and the third have points of discontinuity. The first one would have a point of discontinuity at -2. And again, that's where my denominator would equal to 0. And the second one, I'd have a point of discontinuity at 2. And look at that, that's where our asymptote would be. Okay? So it's all about where x can't be. Think of it that way. In the denominator of the function. If we set the denominator equal to 0 and we solve it, that's where your points of discontinuity are. That is where your vertical asymptotes are also going to be. Now in number 1, we do have a denominator, and if I set it equal to 0, I get x squared equals -1, or x equals plus or minus I. That doesn't help you in the real number system. So it's discontinuous. It is continuous because we're not undefined in the real number system. Okay, so let's take a look at some examples. All right, so what are the domain and the points of discontinuity for each function? Are they removable or non-removable? And where do they cross the x-axis? All right, so I believe, let me see if I have this backwards, and I do. All right, so you know what's going to make life easier if we factor the denominator? Let's do that. Because if we can removable, we might be able to cancel something out. Nope, that doesn't reduce. So this means that we have, let's talk about domain. Domain is x. What can't x be here? Well, if I set them both equal to 0, all right, where x cannot be 3 or 1. That's your domain. Okay? It is discontinuous. It has non-removable because we can't reduce the fraction. Discontinuity. Because it can't reduce it, which means it doesn't have holes. Okay? Now, our points of discontinuity are the same as your domain. So they're x equals 3 and x equals 1. Okay? And let's find our x-intercept. Remember, that means 0 in for y, solve for x. Now, again, this is a fraction, so I always put my 0 over 1 and do cross product, which basically means that 0 equals x plus 3, and x is going to equal negative 3. And my y-intercept is 0 in for x, solve for y. So y is equal to 0 plus 3 over 0 minus 3 times 0 minus 1. Okay, so this is going to be 3 over 3, which is equal to 1. Okay, now just to show you, again, I don't make this stuff up. Okay? All right, so if I put the function into our graph, okay, I'm going to put the original in. Okay, if I press graph, there we go. We have where it crosses the y-axis, which is at 1, crosses the x-axis at negative 3, and we do have vertical asymptotes. See them? So we have points of discontinuity at 3 and negative 3, and I think I can pitch that out. We can see that without the, there we go. Okay. All right, let's try the next one. So let's talk about domain. And again, the first thing I'm going to do is I'm going to set my denominator equal to 0, because that's going to tell me my domain. It's going to tell me if I have any asymptotes. It's going to tell me my points of discontinuity. Problem is that I get plus or minus I. So my domain is going to be all reals because I is not a real number, it's imaginary. Okay? So it is a continuous graph. Okay. It does not have any points in discontinuity. And so we're going to find our x-intercept, 0 in for y, solve for x. And it ends up being just the numerator. So 0 equals x minus 5. 5 is equal to x. And our y-intercept, 0 in for x, solve for y. So I'm going to get negative 5 here. And again, let's check that out in our graph. Okay. So x minus 5 divided by x squared plus 1. Okay, yes, and you can see it is continuous through that part. All right, let's do one more of these. Okay, so we're going to take the first thing I'm going to do, again, I can see that I can factor, so let's start with that. And then I noticed that both the numerator and the denominator contain the factor x minus 4. So we're going to be able to divide that out. Think of it as reducing a fraction, like 2/4. I can divide both of them by 2 and get 1/2. All right. Here I'm dividing both of these by x minus 4, and I'm going to get x plus 1. Now, which means that this particular graph, now we go by the original. Always go by the original for domain. Okay. It's going to be reals, but we still can't have x equaling 4, even though we reduced it down to x plus 1. This has removable discontinuity because I removed the 4. Because I divided by the x minus 4 out. So we have removable discontinuity, and our points of discontinuity are 4. Okay. All right. And our x-intercept is that we're going to go by the reduced form here. And we're going to talk a lot more about this tomorrow. Okay. All right, so let's take a look at what the graph of that looks like. And hopefully I'll be able to, let's try that again. X squared minus 3x minus 4 divided by x minus 4. Okay, so it doesn't look like it's discontinuous, but if I move this over at 4, I kind of zoom in, maybe I can get it to show it. No, I don't think so. But if I put my marker there, okay, it's what it's going to be, which would have been 5. Yeah, it's not going to let me do it. Okay, but if I go to the table, you're going to see at 4, it's no real answer, okay, because it's going to be discontinuous there. Some calculators allow you to see the whole. These don't, because if you think of it as an etch-a-sketch, it can't stop and start, okay? All right, so based on what we just talked about, we're going to talk a lot more about the vertical asymptotes, all right? Vertical asymptotes has a non-removable discontinuity at x equal a. The graph of the rational function will have a vertical asymptote there. Okay, so we saw in a couple of them that we had vertical asymptotes because we had points of discontinuity. We were undefined at certain places in the denominator of our fraction. So here, let's take a look. We're basically setting our denominator equal to 0. Where we're equal to 0 is where your vertical asymptotes. So your domain, like we saw the other day, and your vertical asymptotes are going to be in agreement. They're going to say the same thing. So I'm going to take my domain, or my denominators, set them equal to 0. We're going to solve, and those are where your vertical asymptotes are going to be. Okay. Now sometimes we may have to do a little factoring and so on. Okay, so the minute I see squared and we're going to factor, we should factor. Okay, so x minus 1, x plus 1, and get x plus 1. Now right now, it looks like x plus 1 we're going to have a vertical asymptote there. But we're not, because we can take that x plus 1, divide it out of the function, and get x minus 1 as the function. But we still have to, because x plus 1 was part of the original, we're going to have to leave it. So we don't have any vertical asymptote, but we have our whole at -1 comma something. We're going to have to figure out what that is. Now to figure that out, I'm just going to put -1 over here, and I'm going to get -2. Okay, and we're going to talk more about that. Right now, I just want you to know the difference between a whole and a vertical asymptote. Vertical asymptote, set the denominator equal to 0 and solve. Wholes happen when we can reduce the fraction, and what gets reduced out, that's where the whole is. Now, horizontal asymptotes are problem children. I mean like big time problem children, okay? Because it is really hard to find the horizontal asymptotes. They may say they have it, but depending on the problem, these are seriously problems, children. So we have guidelines. Don't think of these as absolute rules. They are guidelines. And it's based on the exponents of the numerator and denominator. So if the degree of the denominator is m, numerator is m, denominator is n. So if the top is smaller than the bottom, then you have a horizontal asymptote at y equals 0. If the top is bigger than the bottom, we don't have any horizontal asymptotes. And if they're the same, we're going to use the coefficients to see where the horizontal asymptote is. Okay, so I'm going to come over here. And if I look, here are my x's. Notice that they have the same degree. Okay, same exponent, which means I'm looking at this guy. So I'm going to look at the coefficients of those guys. Okay, so that's 2, this is 1. So my horizontal asymptote would be at 2 over 1, or 2. So we would draw a horizontal line at 2, and that's going to be our horizontal asymptote. Okay, here, and again, we're doing this before factoring. I'm going to look at my exponents. Here they are. So I have 1 and 2. The top is smaller than the bottom, so it's y equals 0 is our horizontal asymptote. Again, we're going to keep working on this. I know we've never seen this before, totally brand new to us, and it can get a little confusing. Be patient, you'll get it, not a problem. All right, guys, time is almost up. Please have a great rest of your day. Please take care of yourself. Be safe out there, and I'll talk to you again real soon.